Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 12. Today we're going to talk about linear systems. By definition, we have a linear system of differential equations if the system can be expressed in this form. X dot 1 is a11x1 plus a12x2 plus a1nxn plus f1 of t. x2 dot is a21x1 plus a2nxn plus f2 of t, down to perhaps xk dot is xk1 x1 plus a kn xn plus fk of t. You can see that in this first order linear system, we have all of the derivatives of the unknown functions on the left-hand side. On the right-hand side, we have either constants or functions times these unknowns. The unknowns appear once in the numerator in separate terms. You can't have them multiplied together. That's what makes this linear. And then you have these arbitrary forcing functions here at the very end. In all cases, linear systems can be expressed by matrix equations as follows. Suppose we set x to be the vector x1, x2 through xk. And suppose A is the matrix A11, A12 to A1n, A21, A22 to A2n, AK1, AK2 to AKN, and also suppose that F is F1 of t, F2 of t, through fk of t. With those substitutions, linear systems can always be placed into the form x dot equals ax plus f of t. Here we're using regular matrix multiplication. So let's review matrix multiplication here. If I have a matrix A, B, C, D, and multiply it by a vector xy, what I get is ax plus by, cx plus dy. Here I have a 2 by 2 matrix. It has 2 rows and 2 columns. This is a 2 by 1 matrix with 2 rows and 1 column. Since these match, the multiplication is defined, and the way it's done is you take a row here and multiply it by a column. After you take the entries in the row and multiply those by the entries in the column, you add up the products over here. So the entry, if you take the first row and multiply it by the first column, you get the entry in the first row, first column. If you take the second row and multiply it by the first column, you get the entry in the second row, first column, by matrix multiplication. This generalizes to the arbitrary case. You always get a matrix of this size, 2 by 1. So if I multiply an m by n matrix times an n by p matrix, because these match, the product will be defined, and the product will be of order m by p. I'll motivate this subject to begin with by looking at a second order linear differential equation. We can always turn second order equations into a first order system by making the substitution w equals y prime, which implies that w prime is y double prime. This will become w prime, and this will become w. the linear system that results looks like this. Start with y prime equals w, and w prime equals, we'll have to move all of these terms to the other side. So we get minus p of xw minus q of xy plus f of x. With our second order linear problem, where we had y prime equals w, w prime equals minus q of xy minus p of xw plus f of t, we can write this with x equal to yw, a equal to 0, 1, they're the coefficients over here, minus q of x minus p of x, and f of x will be 0, I guess using x's here, f of x, like this. So we have a linear system that is expressible in the form x dot equals ax plus f of x. This is not a course in linear algebra, nor does it require linear algebra as a prerequisite. However, we need to draw certain facts from linear algebra. So we're going to review some of these things. These are things that you probably learned way back in pre-calculus. If I have a system of equations, ax plus by equals e, cx plus dy equals f, it is possible to solve this linear system by constructing an augmented array as follows. We can perform certain elementary row operations on them. First, you may multiply any row by a non-zero constant. Of course, if you multiply all rows by 0, it makes the whole problem go away and defeating the purpose. The purpose is to find the values of x and y that make these equations into true statements at the same time. So, you may multiply an equation by a constant as long as that constant is not 0, and that doesn't change the solution set. So similarly, you can multiply an augmented array by any non-zero constant. You may multiply any row by a non-zero constant. Second, it doesn't matter what order you list the equations in terms of finding the solution set. Similarly, it doesn't matter what order you list the rows. So you may interchange any two rows. That's a legitimate row operation that you can perform in the augmented array and obtain the solution. Finally, the third elementary row operation, and this is the one that allows you to eliminate variables. If I were to eliminate, say, the x variable, I might multiply the first row by c and the second row by negative a, and then add the equations together. To formalize that process down here on these augmented arrays, you can multiply a row by any constant at all and add what results to a different row. Multiply a row by a constant and add to another row. And that does not change the solution set. The application of these row operations hopefully results in something looks like, say, x equals, let's say, m, and then y equals n. That would be equivalent in the augmented array form to something that looks like 1, 0, 0, 1, m, n. So the goal is to convert an augmented array like this into this form from which we can see with a 1 here and an m here, that's equivalent to the equation x equals m. With the 1 here and an n here, that's equivalent to the equation y equals m. So from this form, which we'll call reduced row echelon form, we may then read the answers. One might alternatively form something that looks kind of like this. I'm just putting blobs here because I'm not concerned about what those numbers are. If you put the system into this form, where you have some other numbers than 0 here in these spots, this is called row echelon form. When a system is in row echelon form, you have each row that does not consist entirely of zeros, beginning with what is called a leading one. Below leading ones, you must have zeros. Above leading ones, you can have anything in row echelon form. The system in row echelon form can then be worked back to find the solution to the original system, but you have to use something called backward substitution. In this case, if we have m and n here, we'll have y equals n on the last row, but x plus some constant times y equals m on the first row. However, once you found what the y variable is, you can substitute back into the previous equation and then solve for x. This is called backward substitution or back substitution. When you work towards row echelon form and then use back substitution, you're performing a process called Gaussian elimination with backward substitution. Alternatively, if you go all the way to reduced row echelon form, where you can just read the solution off immediately without backward substitution, we call that Gauss-Jordan elimination. Let's perform a little example. Suppose I start off with the system of equations 4x plus 3y equals 5, 2x, let's say plus 2y equals 7. We can place this into an augmented array 4, 3, 5, 2, 2, 7. Now, note that I can switch first and second rows. Row 1 and row 2 get switched. I can then multiply row 1 by -2. -2 times row 1 plus row 2 yields a new row 2. That gives me the augmented array. -2 times 2 is 4, plus this is 0. The first row stays the same. But now I have a 0 under this. I'll multiply this through by half eventually, giving me a leading 1. -2 times 2 is -4, plus 3 is -1. -2 times 7 is -14, plus 5 is -9. We can now do two elementary row operations. Let's do 1/2 row 1 yields a new row 1, but also negative row 2 yields a new row 2. So negative row 2 is in its final form. Row 1 is going to become 1, 1, 7/2. This is now in row echelon form, but one more operation places it into reduced row echelon form. Reduced row echelon form requires that you have zeros above leading ones as well as below. So to put this into reduced row echelon form, we need to multiply row 2 by negative 1 and add to row 1, yielding a new row 1. We'll have 9 here. It's negative 1 times this plus this. Negative 9 is negative 18 halves, plus 7 halves gives you negative 11 halves. So our solution will be x equals negative 11 halves, y equals 9. How can we show that this is a solution to the original equation? We can just substitute in. On the second equation, 2 times negative 11 halves is negative 11. 2 times 9 is 18. 18 minus 11 is 7. 4 times negative 11 halves is negative 22. 3 times 9 is 27. 27 minus 22 is 5. So this is, in fact, the solution to the original system of equations. So by going through this process, applying elementary row operations until we get to either row echelon form or reduced row echelon form, we may solve systems of equations in this form. In this way, we're applying either Gaussian elimination with backward substitution or Gauss-Jordan elimination. If one of the rows, one of the equations in a system of equations is expressible as a linear combination of the others, then through a sequence of elementary row operations, you can get an entire row of zeros. So for example, let's suppose we have x plus y equals, say, 2, 2x plus 2y equals 4. The equation starts off in an augmented array, 1, 1, 2, 2, 2, 4. By the elementary row operation, negative 2 times row 1 plus row 2 yields a new row 2. We obtain 1, 1, 2, 0, 0, 0. You can see then we have dependent equations. This equation is basically just a multiple of the first one, and so it contributes nothing to constraining the solutions. It can be just crossed out and eliminated. If you know that a system is dependent, especially if you have only 2 equations, and you know that one of the equations is dependent, you can just cross the second equation out. You don't need it. Or the first equation. But you can always cross one of them out if you have 2 equations and you know that they are dependent. As we've already discussed, for matrix multiplication, if I have, say, A, B, C, D, X, Y, Z, L, M, N, the product is defined by taking rows in the first matrix and multiplying onto columns in the second matrix. This is 2 by 2, this is 2 by 3. Since this match, these numbers match, the product is defined. The product will be a 2 by 3 matrix. It'll be AX plus BL, that's this times this, AY plus BM, AZ plus BN, CX plus DL, CY plus DM, CZ plus DN. If A is the matrix A11, A12, A1N, AM1, AM2, AMN, this matrix has M rows and N columns. If B is the matrix B11, B, we'll make this so that the product is defined, N1, B1P, BNP. So this matrix is N by P. The product A times B is certainly defined because N and N are the same. And the product will be M by P. However, it does not necessarily follow that the product B times A is defined. A times B may be defined, but B times A may not be defined. which is an important lesson in the fact that matrix multiplication is not commutative. It may not even be defined when you reverse the order of a product. However, if we denote this by A, I, K, and this by B, K, J, we can write the product A times B as follows. It's the matrix with entries, the sum, as K goes from 1 to N, of A, I, K, B, K, J. This will give us the ijth entry in the product. Notice that these indices match, and we are summing on that inner index. Let's do some simple examples. Suppose A is the matrix 0, 1, 0, 0, and B is the matrix 1, 0, 0, 0. What is A times B? 0, 1, 0, 0, 1, 0, 0, 0. When we multiply over here, 0 is multiplying things in the first row, 1 in the second row. So we'll get 0 here, and then 0, of course, in the last row. Since both of these are 0, the last row is going to be 0. Here we get a product that is equal to what is called a zero matrix. We might even write this 2 by 2 zero matrix as a zero matrix with kind of a capital theta. On the other hand, let's look at B times A. That's 1, 0, 0, 0, 0, 1, 0, 0. In this case, the first product is 0, but the second product is not 0. We'll have 1 times 1 plus 0 times 0. That leaves 1. And then, of course, in the last row, we get zeros. So I want you to note well, NB stands for the Latin phrase nota bene, or note well. AB in this case is not BA. So in general, matrix multiplication is not commutative, even if the products are defined. The situation is somewhat even worse than this. That 0, 1, 0, 0 times, say, 1, 0, 0, 0. As we've just seen, that's 0, 0, 0, 0. Let's write this as 0, 1, 0, 0. And instead of this, we'll write 0, 1, 0, 0. What product is this? 0, 0, and then, of course, 0 and 0 in the second row. If we call this matrix A, this is matrix A. If this is B and this is C, we have AB equals AC. In usual algebra, for real numbers, if you have this kind of an equation, you can divide both sides by A, canceling the A off, and deduce that B equals C. But as you can see here, B does not equal C. What is the moral of this story? The moral of this story is the cancellation principle from the usual algebra is false. For matrices. Matrices do not satisfy the usual rules of arithmetic. Matrix multiplication is not commutative. The cancellation principle is false. And there's one other thing you can note from what is already on the board. Here we have A times B is kind of a zero matrix. But A is not the zero matrix, and B is not the zero matrix. From this we deduce that the zero product theorem is false. The zero product theorem says if you multiply two numbers together and get 0, then either the first factor is 0 or the second factor is 0. That's not true for matrices. I'd like to talk about the identity matrix. IN is an n by n matrix with ones on the diagonal and zeros everywhere else. You sometimes write this as in this form. I2 is the matrix 1, 0, 0, 1. We often also write I, leaving off the subscript n. What is the significance of an identity matrix? Let's suppose I take 1, 0, 0, 1 and multiply by A, B, C, D, E, F. When I multiply 1, 0 onto this first column, I get 1 times A plus 0 times D. That just leaves A. If I take the first row and multiply by the second column, I get the entry in first row, second column. That's 1 times B plus 0 times E. And then 1 times C plus 0 times F. And now when we multiply the second row, we'll get 0 times A plus 1 times D. 0 times B plus 1 times E. And then, of course, F here. So if I take the identity matrix and multiply it by some other matrix where the product is defined, it just leaves the other matrix. In other words, the identity matrix behaves like the multiplicative identity for real numbers. Suppose we have a matrix A that is a square matrix. Suppose A, B, C, D. If we had a matrix equation A times X equals B, suppose we're trying to solve for X. How do we get rid of the matrix A? Well, it turns out you can't divide by matrices. Matrix division is not defined. But what you can do is you can multiply both sides on the left by the inverse of A. What is the inverse of 2? The multiplicative inverse of 2 is the thing that when you multiply by 2, you get 1. We'll make the following definition. The multiplicative inverse of a matrix A is a matrix B such that AB is equal to BA is equal to the identity matrix, where the identity matrix has ones on the main diagonal and zeros everywhere else. This is equivalent to how we usually think about multiplicative inverses for real numbers. We need to know how to calculate the inverse to a matrix. To do that, let's suppose that we're trying to solve this equation for x. X is going to be the inverse. The way that we can do this is we can write this as an augmented array where on the right-hand side we'll have each of these columns. We'll perform a sequence of elementary row operations to get this to reduced row echelon form until you have the identity over here and whatever the inverse is over here, which we'll call this B for now. B will satisfy A times B equals the identity matrix. It will satisfy this system of equations. And so B will be an inverse. Notice I've been careful to say an inverse. I haven't implied that there's only one. But we have a theorem. undivided matrix has an inverse. If this matrix has an inverse, we're going to show that it has only one. Then the inverse is unique, so there's only one. The proof is typical of uniqueness proofs. You suppose there are two of something. Suppose B1 and B2 are inverses. Then we know AB1 is the identity matrix, which is also AB2. It follows then that if we multiply by B1 on the left, that we can reassociate the sum Now, because B1 is an identity, B1 times A equals A times B1, which is the identity matrix. And when you multiply the identity matrix onto another matrix, it leaves it alone. We deduce that B1 and B2 are the same, and that's the end of the proof. Because we now know that inverses are unique, it justifies the following notation. If B is the unique inverse of the matrix A, we write, instead of B, we write A with a superscript of -1. It follows then A inverse times A will give you the same thing as A times A inverse, namely the identity matrix. Now, inverses to matrices do not always exist. Suppose my matrix A is the matrix 1, 0, 0, 0. If I take that matrix and multiply it by something, let's say L, M, N, P, and get the identity matrix 0, 0, 0, or 1, 0, 0, 1, I'm assuming that A times A inverse, question mark, equals the identity. Is that even possible? This product is equal to L, M, and then 0, 0. We have the problem with this being equal to this. That can't happen. 0 does not equal 1, which means that no such matrix exists. So this matrix has no inverse, and that's entirely possible. Some matrices don't have inverses. It'd be nice to know a condition that you can easily check to see whether or not a matrix has an inverse. Fortunately, that condition does exist. It's well studied in linear algebra. We'll write this as a theorem. An n by n matrix A has an inverse if and only if the determinant of A is not 0. For a 2 by 2, the determinant of A, B, C, D is, by definition, AD minus BC. You can see you multiply this way and then you subtract the product going the other way. There are many conditions equivalent to a matrix being singular, but let's list a few. The matrix A, assuming that it's n by n, is singular if and only if, first. A inverse does not exist. The determinant of A is 0. AX equals 0, the 0 vector. Here I'm saying 0 is the vector, whereas X is the vector x1 through xn. This has non-trivial solutions. Clearly, if x is the 0 vector, A times the 0 vector will be the 0 vector, and that is always a solution to this homogeneous system of equations. However, if A is singular, it will have others. If A is non-singular, then the only solution is the trivial one. This is going to be significant in our solution for eigenvalues and eigenvectors later. There is an existence uniqueness theorem for linear systems. If A and f of t are continuous, on an open interval I, then there exists a unique solution to the IVP x dot equals a of tx plus f of t x of t naught equals x naught. And the solution is defined on all of the interval I. I'd like to show you how to exponentiate a matrix, e to the power of m, where m is a square matrix. As you may know, e to the power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, from your knowledge of Maclaurin series in Calculus 2. I'm going to define that e to the power of a matrix is the 1 from matrices, which is the identity matrix, plus m plus 1 over 2 factorial times m squared, 1 over 3 factorial times m cubed, and so on forever. For example, suppose I take e to the power of the matrix 0, minus 1, 1, 0. What do I get? Let's call this matrix J. Note that J squared is 0, minus 1, 1, 0, 0, minus 1, 1, 0. When we do this product, we'll get a negative 1, followed by a 0, and then a negative 1. This gives me negative the identity matrix. J cubed, then, is just 3 factors of j. If I multiply this by j, I'll get negative j. And then j to the 4th just multiplies on another factor. We already know j squared is minus I. So j to the 4th will be the identity matrix. Then j to the 5th will be j again, j to the 6th will be j squared, and so on. So it's a repeating pattern. This will then be I plus j minus 1 over 2 factorial I minus 1 over 3 factorial j, and then j to the 4th is I, so you have plus 1 over 4 factorial I, and so on. We can collect like terms. All the i's can be put together. I times 1 minus 1 over 2 factorial plus 1 over 4 factorial, and so on. plus j. J times 1 minus 1 over 3 factorial plus 1 over 5 factorial and so on. Now, to understand where this computation goes from here, you need to recall that cosine of x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus and so on. And sine of x has Maclaurin series x minus x cubed over 3 factorial plus x to the fifth over 5 factorial and so on. If you substitute x equals 1 into each of these expressions, you can see that what you get here is I times cosine of 1 plus j times the sine of 1. I would like to show that the solution to dx dt equals ax, where a is a constant matrix, and let's say x of 0 equals x naught, the system is solved by the function e to the at times x naught. This is kind of remarkable because it shows that we have a complete solution to these homogeneous linear systems anyway. It's homogeneous when the forcing function is identically 0, as it is in this case. So if we can demonstrate this is true, we'll have a complete solution. That solution will be great, but as you'll see, it won't be that great, because it's no fun calculating exponentials of matrices like this. To see this, let x be e to the at times x naught, which is equal to I plus a plus 1 over 2 factorial at plus 1 over 2 factorial at squared plus 1 over 3 factorial at cubed and so on, all times x naught. Note that, first of all, if you plug in 0, these terms go away, and you end up with the identity times x naught, which gives you x naught. That confirms that it satisfies the initial condition. But now you have to prove that it satisfies the differential equation as well. So to do that, we'll calculate the derivative. The derivative of the identity matrix is 0 because all of the entries are constants, and the derivative of constants is 0. The derivative of a times t, with respect to t, is just a. Derivative of the next term, a squared t squared. When you take the derivative of t squared, you get 2 times t. 2 is going to cancel this. You'll end up with a squared t. On the next term, we have a cubed t cubed. The derivative there is going to cancel a 3, leaving 1 over 2 factorial a cubed t squared, because the 3 came down and canceled over here. X naught is constant. If you now factor an a out on the left, you can take one factor of a out, you end up with a times x. And that's the end of the proof, because that shows that it satisfies the differential equation as well as the initial condition. We'll end up having to discuss a lot more linear algebra than we need or want at this level if we pursue the idea of solving linear systems, homogeneous linear systems, using matrix exponentials. So we're going to try something else. We're going to use something called eigenvalues and eigenvectors. So I'm going to make a definition. If V is not zero vector, satisfies AV equals lambda V for some lambda, which could be a complex number. We call V an eigenvector of A, and lambda the corresponding eigenvalue. How are we going to use these to solve differential equations? Hang in there, we're about to find out. But first let me point out, normally when you take a matrix and multiply it onto a vector, it changes the direction of the vector, but not true for eigenvectors. Eigenvectors only get rescaled to a new length by matrix A, and that's what's special about them. The matrix A often rotates vectors. It doesn't rotate these eigenvectors, it merely rescales them. Note also that eigenvectors cannot be zero vectors. Otherwise, this would be true for any zero vector and for all numbers lambda. Every number lambda would be an eigenvalue in that case. That's not what we're talking about. Eigenvectors are non-zero vectors. I'd like to point out the following fact, which we might call a theorem. If V is an eigenvector of A with corresponding eigenvalue lambda, then the function x equals e to the lambda tv is a solution to the differential equation x dot equals ax. So if A is a constant matrix, and we're dealing with a homogeneous linear system with constant coefficients like this, if V is an eigenvector and lambda is a corresponding eigenvalue, you can easily construct solutions by these. It's not a matrix exponential now, it's the exponential of just some scalar, lambda times t, all times this eigenvector V. This would be pretty remarkable if it's true. It reduces the process of solving a linear system like this to the finding of eigenvectors and their corresponding eigenvalues. So let's prove this. So we're going to let x be e to the lambda t times v, where v is an eigenvector with corresponding eigenvalue lambda. Then what is the derivative? The derivative is, derivative with respect to t, it's lambda e to the lambda tv, because lambda is constant and so is the vector v. On the other hand, what is a times x? It's a times e to the lambda tv. E to the lambda t is a scalar valued function, and scalars commute with everything. So we can rewrite this as e to the lambda t av. Now, remember what an eigenvalue and eigenvector is. AV is, by definition, lambda v. The matrix A doesn't change the direction of the vector v, it merely rescales it by the eigenvalue lambda. And of course, since lambda is scalar, it commutes with everything. And I can rewrite this as lambda e to the lambda tv. You can see now that these two quantities are equal, which tells us then that x dot equals ax, and hence the proof is over. This whole idea is going to be moot if we can't find a simple way to solve for eigenvalues and eigenvectors. Keeping in mind AV equals lambda V, let's rewrite this as AV minus lambda V is the zero vector. It might be tempting to factor V out right now, but you can't, because A is a matrix and lambda is a scalar, and matrices minus scalars, that's the subtraction that's not defined. But what you can do is the following. You can insert an identity matrix because I times V is V. So this is true. And a scalar times a matrix is a matrix. So now we'll have two matrices that we can subtract. We can factor out V, but V cannot be factored out on the left because matrix multiplication is not commutative. It must in fact be factored out on the right, like this. So you can see now that we have to solve systems of equations like this, where V, by hypothesis, is not a zero vector. What we have here is a homogeneous linear system of equations where we're looking for a non-trivial solution. Remember, a homogeneous linear system of equations has a non-trivial solution if and only if the coefficient matrix is singular. Singular. Also, remember that a matrix is singular if and only if its determinant is zero. So we're looking for values of lambda so that this equation holds. The determinant is made with a finite number of products. As you'll see, we'll have a finite number of products involving lambda. That makes this always a polynomial in lambda. If A is an n by n, then the degree of the polynomial will be n. As you know from your study of algebra, polynomial equations of degree n have exactly n solutions, including complex solutions and their conjugates, and also including repeated solutions. If you don't count repeated solutions, a polynomial equation in degree n has at most n solutions, and they can be complex. For example, suppose my matrix is 3, 1, 2, 2. I need to solve the system. We need to solve the equation 0 equals the determinant of A minus lambda I. That's the determinant of 3, 1, 2, 2 minus lambda times 1, 0, 0, 1. Performing these operations, you end up with the determinant of 3 minus lambda, 1, 2, 2 minus lambda. You can see in the future, all you have to do is subtract lambda from the diagonal elements, take the determinant, and set it equal to 0. In this case, we get 3 minus lambda times 2 minus lambda, that's this product, and then you subtract the product in the other way, which is 2. Multiplying negative lambda times negative lambda gives us lambda squared. We'll have negative 3 lambda minus 2 lambda is minus 5 lambda, and then 6 minus 2 is plus 4. Notice we have ourselves a quadratic equation. You know how to solve all quadratic equations. This one's particularly easy because we can factor it as lambda minus 4, lambda minus 1. And then use the zero product theorem, which is still true for scalars, to deduce that lambda is either 4 or 1. These are the eigenvalues of this matrix A. We also need to find the eigenvectors. So for the matrix 3, 1, 2, 2, we found eigenvalues 1 and 4. We need also to find the eigenvectors. So in pursuit of the eigenvectors, remember that these satisfy the equation a minus lambda iv equals 0. We may always write this as a minus lambda I 0 as an augmented array, and then solve this by Gaussian elimination, finding the reduced row echelon form. In our 2 by 2 case, you will discover that this is particularly simple. Since we're looking for a non-zero solution, this will always be singular, which means that the rows will be dependent. And since there are only 2 rows, that means you'll be able to cross one of the rows out. In the lambda equals 1 case, this just means subtract 1 from the diagonal elements of A. The augmented array is then clearly 2, 1, 0, 2, 1, 0. Notice I can perform one elementary row operation to get an entire row of zeros here. You may always just cross out the second row if you wish. If it's a 2 by 2 matrix like this, the rows will always be dependent, which means you can always reduce it to where one row is all just zeros. The remaining equation is 2x plus y equals 0 if we assume the vector v has coordinates x, y. You can see that this has infinitely many solutions, but it always has solutions like this. If y is negative 2x, if we choose, for instance, x to be a, then y is going to be negative 2a, because y is negative 2x, which tells me that eigenvectors are going to be scalar multiples of the vector 1, negative 2. Another lesson from this is that in the 2 by 2 case, when you write down the augmented array, you can just switch these two numbers and change the sign on 1. That always gives you an eigenvector. Eigenvectors are going to be just multiples of this. We now need to find the eigenvectors corresponding to lambda equals 4. For lambda equals 4, we'll subtract 4 from the diagonal elements. If we subtract 4 in the next row, it's going to be 2, negative 2, 0. Notice if I multiply the first row by 2 and add to the second row, I get 0 all the way across, which means I really didn't need to write that second row anyway. To get my eigenvectors, remember we can reverse these and negate one entry. And so anything that is a multiple of 1, 1 will be an eigenvector corresponding with lambda equals 4. You can see that pretty easily. If I take 1, 2, 2 and multiply by 1, 1, we'll have 3 plus 1 is 4. 2 plus 2 is also 4, which is 4 times the vector 1, 1. To better develop our theory, we'll need some terminology. We call this the characteristic polynomial of A, and 0 equals the determinant of A minus lambda I, the characteristic equation for A. describe the process for finding eigenvalues and eigenvectors. 1. Solve the characteristic equation. That gives you the eigenvalues. 2. For each lambda, solve a minus lambda I 0 as an augmented array. In doing so, you'll end up with the eigenvectors as solutions to the corresponding linear system.